Hey everybody, welcome back. I'm so thankful for how you guys been sticking with everything, and I can't seem to measure how thankful I am. You know what I need is some measure theory. Let's learn more about measure theory. All right. So before spring break, we discussed measurable functions very briefly, but I wanted to just review that and then give you some results. Well, first of all, the whole idea of measurable functions is we want to be able to integrate things that are a little bit more complicated. For example, the Dirichlet function, d of x, which is 1 if x is in Q, rational number, and 0 otherwise. It's not Riemann integrable on any interval. On any AB. But it turns out it will be Lebesgue integrable. And that's pretty exciting that we're going to be able to do that. And the reason is because this is actually a measurable function. Now, what is a measurable function? A function f from Rn to R, and I'm going to put in parentheses here, sometimes we say union plus or minus infinity to allow the possibility that our function goes to infinity in a few points and stuff like that. But just to make the proof simpler, I'm not going to have that in this lecture. But that is included in the book's lecture. Anyway, I haven't finished my definition. So a function f from R to R is measurable if for all alpha in R, that's just a number, the set f inverse of the inverse image of the set alpha infinity, the open interval, that the inverse image of that is actually a measurable set. Okay. So that this set is measurable. So the idea is that we're using the definition of measurable set to define measurable function. So all the these kind of sets, the pre-images of intervals, will be measurable. And there's an important lemma here, because it turns out I really could have defined this like a bunch of different ways. And so let me tell you about those different ways. So first of all, let f from Rn to R be a function. The following are equivalent. So 1, f is measurable. 2, for all alpha in R, f inverse of the set alpha infinity is measurable. Okay, that's the definition I just gave. So, 1 if and only 2 if 2, or that's just the definition. But I've got some more stuff here. So the second version is, let's say for all alpha in R, the set f inverse of closed interval alpha infinity is measurable. And we can actually do the same thing and but go from negative infinity to alpha. So these are equivalent characterizations of what a measurable function is. So f inverse, I could go negative infinity to alpha with an open bracket. And then the last version is negative infinity to alpha with the closed bracket. Let's measure that. All right. So let's do some parts of the proof. Well, let's see. One is true if and only if two. Why is that true? That's right then. Definition. Good. All right, so now let's look at let's show why 2 is equivalent to many of the other ones. So, can anybody see why 2 is equivalent to 5? That's right, Shaylin. Yes. It's because this set is the complement of that set. And so you can use the fact that the complement of a measurable set is measurable. Well, actually, in order to prove this, we need an interlude. This is a set theory fact. For all functions g from a to b, any sets, if you take the inverse image of, let's see, I have to call this set in here, and let S be a subset of B. Then G inverse of S complement is the same thing as G inverse of S complement. Why? Well, you actually just compute the two sides. So let's look at G inverse of S complement. Well, that's the set of all x's such that G of x is in S complement. And then this is the same thing as the set of x's such that G of x is not in S, right? Well, okay, now let's compute G inverse of S whole thing complement. This is the set of all x's such that x is not in G inverse of S, right? So the complement. And then what does that mean is that that's the same thing as the set of all x's such that G of x is not in S. And look, it's the same thing. So that's why, right? So that will color a little bit of interlude. And now we can actually look at 2 and 5 and show that they're the same. So if we have, for all alpha in R, f inverse of, let's see, this is the open interval alpha to infinity, is measurable. This is true if and only if its complement is measurable. Right? That's right, Caleb. Good job. So but that is the same thing as saying, that's right, Lucas, f inverse of alpha infinity complement is measurable, which is the same thing as saying, Peter, right, f inverse of negative infinity alpha is measurable, which is 5. Just as Schilling predicted. Right. And for the same exact reason, these two are equivalent. Let's see. 3 and 4 are equivalent, right? Okay. Because one of the, let me just show you what the 3 and the 4 are, right? Because those two sets are complements of each other. So, all right. Good. All right, so let's see, what about 2 implies one of the other ones, like 3, okay? So let's look at 2 if and only if 3. Okay, well, 2 says that for all alpha, f inverse of alpha infinity is measurable. Okay? But then that implies that this set, which obviously would be the first one you would think of, is that right, Peter? Yes, I thought so. If you take this set complement, so this, if 5 is true, it must be, this must be measurable, because 5 is this one, right? So this is true if and only if 5, which implies that this is measurable. Because that guy is measurable, and then you take a union, countable unions is measurable, and then you take a complement, it's measurable. All right, but look at what this is. This is the union of the inverse image of all those things, which is the same thing as the f inverse image of the union k equal 1 to infinity of negative infinity alpha minus 1 over k, close bracket. And this is the same thing as, then, right, good job, as negative infinity alpha. Because see, this is just a little bit less than alpha, and then as k goes to 0, it gets closer and closer to alpha. So, right. And, which is, yeah. And then this is measurable, which is equivalent to, let's see, which one is that? That's 4. And that's, well, yeah, that's equivalent to 4, which is equivalent to 3. All right, so I've, then you also have to go the other direction, but you can also do a similar argument that 4 implies 2. So, and then you get QED right from that. So all those things are the same as, all these guys right here are the same as just f is a measurable function. So, for example, since if you look at d of x right here, then d inverse of alpha infinity, what is it? Well, it either equals, let's see, q or all of r, right? And this is if alpha is greater than or equal to 0, and this is if alpha is less than 0. So this set of points that land in alpha to infinity Oh, actually, yeah, that would be okay. And alpha less than 1. And then it's the empty set if alpha is greater than equal to 1. Yep. If alpha is greater than equal to 1, none of the values of d are in there. But if alpha is between 1 and 0, then you get all the rational numbers. And then if you put the alpha less than 0, then everything is, it gets maps to those points. And so it's the whole. So all of these guys are measurable. So therefore, D is measurable. Okay. And it turns out, like for instance, all continuous functions are measurable. All continuous functions with a finite number of discontinuities are measurable. So it's good stuff. All right. So there's a lemma that goes along with these measurable functions. And I'm going to call this the algebraic measurable function theorem. So suppose f and g go from Rn to R, and they're both measurable. Then the absolute value of f is measurable. F plus or minus g is measurable. F times g is measurable. I also could divide, but then I'd have to be careful of if they land at 0 or something. If f plus and f minus are measurable. Okay, so what are these things? I have to tell you that f plus is the positive part of f, and then the f minus is the negative part of f, but they're both made to be positive functions. So f plus of x is defined to be the f of x if f of x is greater than or equal to 0 and 0 otherwise. And f minus of x is defined to be equal to f of x, minus f of x, so it makes it positive if f of x is less than 0 and then 0 otherwise. I could have put greater than there, it wouldn't have made a difference. So anyway, so these guys, and by the way, so f equals f plus minus f minus. So that's used a lot in measure theory. And we'll see pretty soon that absolute value is actually measurable. Why don't we prove that? All right, so A. Well, suppose f is measurable. Then what we need to look at is the absolute value of f inverse of alpha infinity. So that is the set of, we've got to take different cases, I guess. So let's see. Well, if it's actually sometimes all of Rn, when would that be true? That's right, Joe. If alpha is less than 0, right? And let's see, what about the next case? What if alpha equals 0? And that would be, that's right, Lucas. It would be the set of all x's where f is not equal to 0. Because that would be the only case. Right. Right. because that would be the only case you wouldn't be in there if it equaled 0. All right, because otherwise it's 0 positive. Good. All right, so now if alpha is greater than 0, it's all the f of x's that are, it's all the set of x such f of x is greater than alpha, or what's the other case, Shaylin? Right. Or f of x is less than negative alpha. All right. But, okay, so this guy is measurable, no problem. What about these guys? Well, that's actually can be written as the second guy. Why don't we call this number 2 and this number 3? Number 2 equals the set of x such that f of x is less than or equal to 0, intersect the set of x such that f of x is, oh, wait, I was doing equals 0. Oh, okay. And then complement. Okay. It's the set of x's where this is less than 0 or this is greater than 0. And let's put union. Okay, there we go. Is that what you meant, Shaylin? Thought so. Okay. Anyway, right, because that would be that. All right, and this is measurable because it fits one of our categories, and that's measurable. Right, that's the alpha equals 0, and that's the one where you go up to 0, alpha being 0. Right, not that, right? So that's measurable. So that one's good. Okay, what about 3? So, yeah, I mean, again, it's a union. So it's the set of x such that f of x is greater than alpha union set of x such that f of x is less than negative alpha. And this is measurable. This is measurable. So in all cases, absolute value of f inverse of alpha infinity is measurable. So therefore, absolute value of f is measurable. Great stuff. So that's the QED for part A. Well, and then you could prove all the other ones too. Now I wanted to tell you another lemma, another way of combining measurable functions together to get more measurable functions. So suppose we have a sequence of measurable functions. Suppose fk, k from 1 to infinity, is a sequence of measurable functions on Rn. Then all the possible things we can do with the sequences are measurable. So the nth over k of fk be the sup fk. So in other words, what this means is that nth over k of fk of x is the nth over k of fk of x of that number. So it's the infimum of those numbers at every x. Okay, so that's that one. Okay, so that's another thing you could do. You could take the lim nth k of fk at each x again. You could take the lim sup at each k of f of x at each x, and these are all measurable. And so just for an example proof of this fact is that if you look at sup of fk inverse image of alpha infinity, this is the same thing as the union k equals 1 to infinity of fk inverse of alpha infinity. So in other words, it's all the x's where fk goes into that range, and over all possible k's. And then you've got it covered, then the soup has to be in that range. And then on the other hand, if you take something in here where that's the soup, then you've got values of fk of x that are getting close to that. So they're both the same set. So, and then these guys are all measurable. So you take their union and the result is measurable. So, anyway. Let's see some pictures. Oh, yeah, I wanted to mention that it's not necessarily true. So this is a weird fact. It's not necessarily true that the composition of measurable functions is measurable. And also it's true that you could take non-measurable functions and add them together, compose them, and then you get something that's measurable. So, yeah, so that's a thing you got to watch out for. Well, that was fun. Now we can take those measurable functions and integrate them into our lives next time.